So in this question here, what I want to do is expand a complex number to the power of 5, but this time in the denominator. So 2 plus 3i to the power of 5 in the denominator, that's equivalent, let's just write it here, to 2 plus 3i to the minus 5. Now what I want to do is express the result of that, when I've expanded it out, in the form of a plus bi, the real and imaginary part, the exponential r e to the I theta, where theta is the argument and r is the radius, and z equals r cosine theta plus I sine theta, where theta is the argument and r is the radius, a bit similar to this one. If you get this one, it will normally lead you to this one. So these two will kind of come together. One will become free if you get the other one, and then this one will need a bit of work. So to expand this out, what I can't do, because it's not a positive power of, or a positive integer power of 2 plus 3i, I can't use DeMoivres Theorem, which is a bit of an expansion of this one. So what I've got to do is try and expand it out by hand myself. So what I'm going to do is I'm going to rewrite this in a way we can perhaps expand it out on the board here. So as it's to the power of 5, I've got squared, squared, and then plus one more. So 5 lots of 2 plus 3i. So I'm going to rewrite this as 1 over 2 plus 3i. And then what I'm going to do is 2 plus 3i squared, and then quantity squared. So that's what I'm going to do. So to expand this one out on its own shouldn't be a problem. And then I'll end up with a real and imaginary part, which I can square again, just like I did here. So let's go with that. So now 2 plus 3i, going to keep that. Let's expand this bit out. So there's that one times that one twice will give us 12i. Then 3i squared is minus 9. And 2 squared is plus 4. So that was pretty straightforward. Then I can just simplify this and then square again. 2 plus 3i, and then 12i minus 5. And that's squared. Okay, so just like I did to get from here to here, I'll do the same with this one. So then 1 over 2 plus 3i. Let's go with this one. 5 times 12i is 60. With the minus, it's minus 60. Twice, that's minus 120i. And then I've got 12i squared, which is minus 144. And minus 5 squared, which is plus 25. Okay, so let's simplify that off and then multiply it with this. So let's just do it here, save writing it out again. So I've got minus 120i, minus 144 plus 25. That I can just cross out and put minus 119. And then I can just multiply off as we would do normally with foiling with real numbers. So then I've got 2 times minus 120i, that's minus 240i. 2 times minus 119, minus 238. And let's deal with this 3i. So 3i times minus 120i, that's going to give me positive 360. And then I've got 3i times minus 119, so that's minus 357i. Okay, so now what have I got now? I've got 240i minus 357i, so that's minus 597i. So 1 over minus 597i, and minus 238 plus 360, that's going to give me positive 122. Okay, so now what I've got here, I want to get this into this format. So with this in my denominator, that's not going to work for me. So what I want to do now, I want to try and get some complex conjugate in here, and then try and get a number with a complex number on the top, and then there's all real numbers in my denominator. So let's bring this up here. So 1 over 122 minus 597i. So multiply that by its complex conjugate. So if I have 122 plus 597i, and then the same. So basically I'm multiplying by 1. So good old trick there. used in all kinds of analysis. So my denominator will stay as that. So 122 plus 597i. And then what I've got to do now is do 122 times 122. So I'm going to need my calculator for that. So 122 times 122, 14884. And then the two imaginary numbers multiplied together. So 597i times minus 597i. That's just the same as doing 597 times positive 597. I's will cancel out. So that will give me 356,409. And then what will happen is, if I multiply this with this, and then add it to this with this, they will cancel out because one's positive and one's minus. So that's the trick with complex conjugates. Okay, so now, ready now to write this out, if I can add these two numbers up on the bottom. So 14884, let's get the calculator out again for that one. So plus 14884. So that's going to give me 371,293. Okay. So now what I can do is I can split this into its real and imaginary component by just splitting the fraction. So I've got my A value will be 122 over 371,293. And then my imaginary component, I'll just put an I there. Then 371,293. And then 597 for my B component, 597. So my B component is 597 over that, and that's my A component. So that's the first part taken care of, so I'm happy with that. Now we need to work out the radius and the argument. Now the radius will come from the beginning part. So if I draw that up on our complex plane, let's just draw it here. So 2 plus 3i. So that's my real, that's my imaginary. And I recommend you guys do this with all complex analysis just to see what's going on with complex numbers. The real part is 2, imaginary part is 3. So that's our radius. So then to calculate that, simply Pythagoras' theorem. So we've got a 3 there and a 2 there by the real and imaginary. So the radius is square root of 13. That's pretty easy to see there. So the radius of this is now square root of 13. But remember, this is in our reciprocal version. So basically what we've got is 1 over root 13 to the power of 5. So r equals 1 over root 13 all to the power of 5. So that will give us, raising that to the power of 5, well, 13 squared, sorry, root 13 squared is 13. Square that again is 169, and with one more root 13. So r equals 1 over 169 root 13. So that's our radius. Now we need to work out the argument, i.e. theta, or theta value. So theta is normally given as the inverse tangent of the imaginary part divided by the real part. And in our case, because we've worked it out here, this is our inverse tangent inputs. That's our real, that's our imaginary. So we can cancel these out if we like, but I'm going to put it in here so you can see what happens. So we can see that they are actually included. 597 over 371,293, all divided by 122 over 371,293. And you can see that this big 6-digit number is going to cancel out. And then in which case theta is the inverse tangent of 597 over 122. So that takes care of that. Now, to put that and try to approximate that to pi is going to be very difficult, but you can find its radian version, which is approximately 1.369. I'll let you guys check that. There's a lot more decimal places, but that's our approximation of theta in radians. So with that, we are now ready to finish off these two parts. So z equals r e I theta. We've got r and we've got r theta, the exact and r approximation. So I'm going to write both up. So now I'm going to give myself a bit of space. So I've got 169 root 13 in the denominator. And then e to the I, theta, inverse tangent. Remember, this is in our exponential input. 597 over 122. And then we can approximate that. We can keep this, that's fine, because we know that's good. And then our approximation of the input for theta, so e to the I, 1.369. And now we can do that part there for this bit. So then giving ourselves a bit more space again, 1 over 169 root 13. And then we've got, that's our r, and then cosine of theta, so it's cosine of that. So cosine of the inverse tangent of 597 over 122, and then plus I sine inverse tangent 597 over 122. Just trying to squeeze that in there. And so that's all in there as well. So bigger bracket just to close that bracket off. And then now the approximated version. 169 root 13. Cosine. Now we don't need to worry about the inverse tangent here. 1.369. Plus I sine 1.369. And that completes our answers. So that's this one here. That's this one here. And that's this one here. So you can tell me in the comments which methods and which techniques you prefer, which actual result you prefer. But that's how we go about solving that for a negative power with an expansion of a complex number. Okay.